All right, this video here is going to be about the final operations on the spiral part and explaining the planning and setup of the job like I promised in the first video, but I'm making this because it's not really a video that the general public, my viewers of my channel, will be interested in this because they said so in many of the comments of the video of actually doing the second operation, machining on the spiral part. But the reason I call it the spiral part too, let's just say that, because if I give the real names of these parts and these people that we're doing them for, watch the videos, they make me take the videos down. So I just have to make up some name, spiral, helical part, whatever. But it's just a name I pick to make that clear. It's not really the actual name of this part, and I don't really even know what this part does. A lot of comments have been on what does that part do and everything, and I don't really know in the case of this part. So that, and I really can't even tell you, because otherwise their legal departments get on me and everything. They kind of tolerate me doing this much of a video on it, but I can't really give a lot of information on these parts, because then the attorneys contact mostly Centerline, because that's what this job is for, and then I can't show my videos. So you kind of have to work with me on that kind of stuff. I can't really. But in this case, I don't know what this part does, so I couldn't tell you even if I wanted to. So anyway, back to what I was saying. This video is going to be about that, so there's going to be a lot of information in this video that the general public won't even watch the video. They'll click on it, click away in 30 seconds, and nobody sees the video. So these kinds of videos are not that interesting to anybody but people who watch my channel, subscribers and stuff. And I said I would make a video about my planning and setup of this job. So that's what this video is going to be about. But I also wanted to talk about some stuff that's going on here at the shop. Right now, the situation has kind of changed here. How do I explain this? The original agreement with me and Centerline Manufacturing of moving some machines in here and working on some projects they wanted me to do was also that I would ultimately sell my machines to them after a certain period of time, which this period of time has ended up a lot longer than I figured it would. But it's come to the period of time where I actually sold my machines to them at the end of August. So the kind of break-in videos that we've been seeing has been due to the fact that I'm actually working for them now, and I can't really be making a lot of videos at the same time I'm being paid by them to do work, if that, obviously. But they don't really mind if I do some, as long as I'm getting the job done, because they've actually benefited from me doing videos in the past on certain jobs, on the jobs that I was doing and getting paid for, but they were mostly their jobs. But I was I don't know what you call it, like a contractor, or they were jobbing this job out to me as another machine shop. But now the situation is kind of changed, and I can't really do it that way anymore. But I do have the machines in the garage, and I haven't really been out in my garage in a long time. I went to do something on the Haas mill, and I noticed the fourth axis is acting up, which I think is probably due to bad connections in the cabinet. But I haven't even troubleshoot that, so I've got to work on those machines, and I can still make videos in the garage, which would actually more relate to a lot of the people that view my videos, kind of like what they do with their hobby shops and stuff. And I will continue to do that up to the point where I actually move down to Mexico to live down there, which that's not determined yet, so I can't really say. But all of this has to eventually move forward to getting down there to Mexico. And if I can, I'll probably set up a little shop of some sort down there, like what a lot of my people that subscribe to my channel do is, they work in their garage and things like that. If I can. We'll have to see on that. But anyway, So that's a kind of a brief description of why we've had a gap in videos I've been making, because I can't really do it the same as I was doing it, because it was my business and I wasn't working for somebody. So anyway, let's look at what's going on here with this part. All right, here's the part, or the customer supplied model for this part. Now, like I said, I don't know what this part does or anything about it. So if you ask me, I can't tell you, but I probably couldn't tell you anyway, or that causes me problems with being able to make these videos. So, you know, if you want to ask, fine, but I can't tell you anything about it, even if I knew, which I don't. So their drawing said to machine it to the model. It's pretty rare to get a note on the drawing saying that. And if there's any engineers out there watching my videos, if you're going to do this kind of thing, kind of make sure that the model is drawn properly. I tried to fix these problems, but you see this little extra surface in here on the intersection of these spiral parts of the model to this OD. It's got these extra little imperfections in the model here. If you could see it right there. And this causes a lot of trouble with the CAM softwares when you have these. And I tried to correct that, but I couldn't seem to get it to my software. I couldn't correct it. They've also specified a corner radius of 1/4 of an inch between these intersection points. And it would have been better to have that 1/4 inch in there rather than not, because I could have used a smaller end, maybe a little bit smaller radius, tip radius end mill or something to make these intersections in the programming of the part. So just kind of keep that in mind. Your model has to be accurate, and also it has to be drawn to the middle of the tolerances if possible, because that kind of creates an issue when you're programming it in the CAM software. You have to know that. So the first thing I usually do when I'm planning out a job like this is I inspect the model and I try to correct any errors and check the dimensions of things to make sure that it's actually drawn in the middle of the tolerances that we're kind of going for. And also it's kind of unusual, this particular part has this off-center hole through it, and you would think that, let me just get a straight on view of this, that this would be some kind of round OD on here, but it isn't at all. You can see there's kind of like a flat in the middle of it, or it even dips down right here with this. Otherwise you could almost turn this OD here where these surfaces are, but they're not really round. There's a bunch of little surfaces in here. So that was something that had to be accounted for in the machining. But also this I'm not doing the square holes. That we're going to send it to have a wire EDM. The center line has some wire EDMs, and they're just going to have it cut. I just drilled a hole through here so they could start the wire, as you saw in the first video. So anyway, the stock starts out like this, and there was an off-center hole drilled that was 4 1/4 inches in diameter, and it's the distance between here and here I think was 540 thousandths, if I measure it, between the two center lines of the holes. So that's the way it was supplied to me, and I had to finish it to the overall length. It was a little bit longer, like a 1/4 of an inch long. So in the first operation, although I didn't show it in the video, what I did was I took that stock and I turned it down on this one end. I was supported in the tailstock, and I put it in the four-jaw chuck and got it to run off center the appropriate amount, and I turned it down and I mounted one of my rings, which you'll see in this other drawing, I'll show you in a second, on here, and supported it on the steady rest, and then backed the tailstock off, and I bored this bore 50 thousandths under the finished dimension, which later turned out not to be necessary. But the material, as I go back here, being 17.4, and it's already heat treated, I think it was a condition 1075 if I remember right. a lot of times when you do stuff like this with a bar, your bar is starting off like this and you're putting a hole through it off center, and then if you split it down the length of the part like this, it's going to change in size. And I kind of expected, because this OD here is going to be kind of in compression, and if you put a hole off center, it's going to have more compression force due to the manufacturing of the round bar here, and you're reducing it here, and the thing's going to contract or close this round diameter down after I split it. So I was kind of expecting all that. So when I designed the fixturing and such for this, I thought that's going to be an issue. So like I said, I turned it like this and then supported it on the rings. You're going to see the next drawing, and then bored it 50 thousandths underside. So then we came to this situation where I mounted it on this fixture that's mounted in the 4-jaw chuck and the Mazak, and the part sits on here. Now I'm going to explain something here because I had a lot of questions about this. Let me cut a section through this right here. These set screws that hold the part, well, actually they're just for the purpose of aligning the part. They don't really hold it per se. So on the fixture I made, I bored a counter bore, and then I bored a kind of a close tolerance hole, and I machined the set screws so that they'll fit in here and kind of align the part on the threads. Now, I'm not wild about aligning on a thread per se, because the threads have tolerances, the set screw had a tolerance, so it all has to fit. You know, a screw has to fit in a threaded hole. If it was right on the same size, it would never fit, so there's always clearances. And this isn't the best way to line up on a part, but for the purpose of this, the tolerance was dimensioned as far as the spacing of these holes to 1/2 degree, and from this radius out, that works out to be 22 thousandths, I think. So I was feeling all right about that, even though there's going to be a little bit of slop in these screws when I thread them in. And then of course I got to have clearance on this bore the screw fits in and everything. So, but it seemed to be working out all right. At least the first part checked out all right as far as that goes. So what I was talking about here was I was explaining that the set screws aren't really set screws at all. They just thread in here and align on this diameter. And then I put this 832 socket head cap screw. I don't know if I have that in the drawing here. Maybe this? Yeah, in there. And it actually pulls the screw down into the hole. And mostly it's for the purpose of keeping the screw from vibrating out when the milling is happening up here and running, and then run into one of the milling cutters runs into it. So that was the way the set screws worked. There was a lot of comments on the first video about, oh, you're putting a set screw on top of a set screw, but the set screws don't actually hold the part on the fixture. They just align the holes in a indexing alignment, if you will, to the other end of the part. And these little screws in the middle are an additional socket head cap screw to keep the screws held down. They're not really even tightened. If I tighten them against the bottom surface here, it would push the part away from the fixture, and I don't want that to happen. So that was the reasoning behind those screws, and I didn't really explain that in the first video, and there's a lot of questions about that. So the next thing would be these rings that are going to be used for the final operation, really. Let's see if I can show those. So that would be these rings here. See if I can hide this thing here. Okay. And their purpose is just to hold the part, because it'll be split by that point in the down the length, and so you can't really just chuck onto it. You would collapse the part if you tried to chuck onto it, and you couldn't bore all the way through it very easily. You know, how are you going to support this end? Well, actually it's turned around this way in the final operation. And of course, let me turn this stock off here, because that's not going to be that way. So it'd be like this, and this end of it would be in the chuck, and this would be on the steady rest, and these plastic pieces, like you'll see in the video, just keep shavings from getting in between here, because you got the part split in half here, and shavings will be flying out here and getting in the rollers of the tails, the steady rest. So that's the purpose of all of that. And then I even put a piece of silicone rubber held with magnets over the top of the jaws, so J-beams won't come over the top and fall in between the rollers. So that's what these things do here. And I bore it all the way through with the silent bar on the final operation. But I thought, like I said, I thought I was going to have to straighten this thing, so I designed this straightening device, which is here. And I was going to use this Interpack cylinder and expand it out, so it would be opening the tube up, if you will. And if for some reason the tube opened up when I split it, then I could just put it in the press and compress it down very carefully. But this turned out to not be necessary for these parts anyway. I'm not saying that wouldn't be necessary if there's any future parts, because it could very well. But I was planning on making this by just turning this diameter and then having them split this with a wire EDM. And then I was going to put these jack screws in here in case I had to move the part more than the travel of this cylinder or something. But like I say, this turned out to not be necessary in the end, so I didn't make that. So when I'm kind of planning a job, I kind of look at all this stuff and how I'm going to do it, and figure out in my mind before I even start on it how I'm going to go about doing this. Otherwise you could get yourself, backed into a corner and you don't know how to get out of it. So that was the kind of planning aspect of it. I don't know if I'm going to go a lot into the programming part of it, but because everybody's software works a little bit different, and I use this Spree TNG to program with. I guess I could show you a little bit about that. Let me start the software up and I'll show you a little bit on the aspects of that programming. Alright, here we are in the CAM software. Spree TNG is this CAM software. I'm just going to quickly go through the cycles, some of the cycles, not all of them, because some of them we don't care about, holes and things like that, but the milling things are more interesting. And first the turning. So this was as you can see, the stock represented over here from the first operation, which I just turned it and bored it. And then this is the roughing of the end there, and that's the finish cut. And then this is the roughing with the feed mill that you saw in the previous video, and then here's the tool path of that. And this, I believe, is a Z-axis. It's a 5-axis Z-axis roughing, but it's actually only moving. It's kind of keeping the tool on center line and only moving back and forth to do this roughing cycle. You could see all the tool path here of that. Now you can restrict the movement in one, and I didn't want it to tip the B-axis, so the B-axis just stays at 90 degrees and roughs straight in, and it roughs downward in the Z-axis. And with this software, if you have the stock defined, it can take into account the previous stock, which is like this, so that it doesn't put a bunch of extra tool path where you don't need it. So that was the feed mill's roughing cycle there. And then we have these two is just kind of roughing in that flat next to the slot. And then this is the finish cut. And this cycle is it's actually a wrapped pocket with only a floor finish. I was only doing a floor finish on this. It looks kind of funny the way these movements are, but that's because it's kind of wrapped, and that's the way it has to make its rapid clearance movements and such. It's not really, well, you saw it in the video how it worked. So if you don't look at that, and this is the simulation of it, or the stock, because if I unselect that, you can see now here's the stock of what it leaves, and it's leaving these spiral ribs to be finished later. And so the top of the rib is this cut, which if I show it, And I had to do it that way because, like I showed previously, it's not really round on the OD or anything, and you can't, well, even if it was round, these areas where it tapers in, you still have to machine them, even though you could turn the OD, but it's not really, it kind of has an odd shape to it. I don't know what the part does, so I can't even comment on that, but see, it takes these scallops off the tops of the ribs, these two cuts here, and then these are the 5-axis swarf cuts. These are a swarf cut. And really it's not, it's kind of just rotating and moving in Z, because the X, if you will, although that's not really X on a 5-axis cut, is not really moving. It's just coming down to this OD, or, well, these are the rough passes here, if I show them here, and then there's a set of finish passes, and I go over it again, and I move in closer and finish it. Now, just looking at one of these, let's go over to the simulation part. And the reason I'm showing this is because how do I figure out how long I need to make this fixture stick out so that the machine axis clears everything, this, and particularly this back here where this cabinet is that covers the y-axis. And the way I do that is I kind of put the part in here in the CAM software, and I simulate it, and if I get a collision up here on either end of it due to the travel of the machine, then I can say, okay, I got to move the part out, and in the part setup part of the CAM software, I can move it out until I don't get a collision anymore, and then I can figure out how long that has to stick out in order to do that. So that's kind of the way I figure that out. And you know, when I'm doing the initially doing the programming, you can't, it's kind of hard to tell when you're doing these kind of cuts where they're going to actually end up. See, as far as it is right up in here, or further up here on the machine, and that's the way I usually figure that out. I actually program it, and then when I run the simulation, I can see collisions that happen depending on where it's going. So that's what I do there. And so those are the 5-axis cuts, and then the rest of this is pretty just straightforward machining. The radiuses on those corners and so on. And then there's just the holes around the OD here. There's nothing really special about that. That's just regular standard programming. Seeing if there's any, for the engraving, I just took, because this guy, whoever modeled this part actually modeled these, and I just made them into pockets, and I just engraved them the way they had them on the model here, as well as these other ones over here. That's the way I did that, although in reality that wasn't the most efficient way to do it, but it took some time because of the way the pockets and the toolpath is very, I don't know, it just took some time, but it did work. And for only 3 parts, I wasn't too worried about it. If I was doing a lot of parts like this, I would actually use a real proper engraving cycle for that. Doing these tabs, because this isn't just a straightforward tabbing operation, which you can use because of the radius of the bore intersecting the tabs, so you can't just go down to a certain level and cut in here, because you're going to actually cut the part off before you want to, because of the bore being radiusing up into the tabs. So if I just went down to this level, it would part it off. If I go down further somewhere here, so I had to kind of program those tabs manually, if you will, or so that it would not just cut the part off. And you see, I had to kind of program down and then move up in Z and down, because if I just stayed at this level, it would have parted the part off of there. If I tried to tab it like a normal tabbing operation where it was real thin here where the part is, it would have cut it away up here where the bore arcs up into the tabs, if that makes any sense. I don't know. So I did it this way, and I'm just moving up and down in Z like that. and I had to kind of rough these slots in here so that I could do that, because I'd be plunging down into solid metal, so that's the way I did it. And to make the tab as thin as I could next to the part here without actually parting it off. So because of the bore and everything, that made the tabbing operation a little bit cumbersome to do. But so that's the CAM software stuff. I don't want to really go into tons of detail on the actual programming aspect of this, because that's just not what this video is intended to show. You know, as far as these swarf cuts in Esprit, you have to do them a certain way. You have to define ruled surfaces and things, and then the machine knows to tip the spindles and everything to do it. And like I said earlier in the video, those little surfaces down at the bottom there made that kind of difficult to do that, because of the imperfection in the solid model, as well as this roughing operation here. It kind of made it difficult, because you have to define in order to miss certain things. Well, actually it was this wrapped pocketing that was the trickier one, because I had to define places not to machine in the wrapped pocketing, or the wrapped pocketing, and that made it kind of hard to define them, because there was an imperfections in the model down there. So anyway, that's just a real quick look at the CAM software. We finished all the milling operation up to this point, and we have these tabs to cut through. I did this because I was worried about distortion when the part, when I milled this away, but it turns out that the part stayed on size, so I didn't have to do all this, but you never can tell. It might spring one way or the other. So what I did was, on the first two parts, this is the third part actually, is I just cut these tabs with the grinder to get them cut away. So like this. I just cut through all of it. Sort of taking care not to hit this is actually a finished dimension, except for where the tabs are almost finished. I don't want to hit that with the cutoff wheel. So kind of trying to do this in a way that this part just doesn't go flying. Kind of tricky. I'll rotate this thing a little bit. It's the last cut you got to worry about, of course, when this thing falls. So I'm going to save this tab for the last one to cut off, so it falls away from the cutoff wheel. And now it's loose. I got to cut this last one. Hopefully it doesn't go flying. All right, now take this out of here. Now what I did on the first two parts was just leave this all alone and rotate back up to my C, in this case 180 degrees, and I just manually jog the machine through to trim these tabs off rather than taking the part off and trying to carefully grind and file them. It turned out because the part didn't spring in or out. In fact, should be able to check that. Let's see. As far as the width here should be 2 inches, or very close to 2 inches. What's within a, kind of hard for you to measure this that way. If I rotate it down a little bit. It's within a couple of thousandths. The tolerance is like plus or minus 5 here. So it'll be all right. So now I got to rotate to 180 and index the B-axis down to 90, and I just like I said on the first time I did on the first two parts, because I wasn't sure this was going to even work, you know, that the part was going to spring and I was going to have to straighten it or something before I did all this. So there's the 180 according to my display, and what I'm going to do is so I don't accidentally make a mistake here in jogging the the C-axis, I'm going to clamp it. And that way in the manual mode you can't rotate the C-axis. Even if you put it on C-axis jog, it'll give you an alarm saying that the axis is clamped. So what I did is I came over here, and I know this happens to be 0.875 off center to get to this the right width, or 875, 876, because the end mill is not exactly 1/4 of an inch. So I put it on 0.870. I get this over here and I just make sure I got the right depth set. Kind of hard to see this when the doors are closed, how deep you got the tool going. Okay, like that. Okay, we got the tabs trimmed off of here. Kind of deburred this edge a little bit. And now, to take the part out and get the rest of the setup made for boring the ID here, because I left it undersized. Now it turns out that I really didn't need to do that. After I took the first two parts off of the the end plug and off this fixture over here, turns out that the part didn't change in size or hardly at all. Not enough to worry about, but you never can tell. This is by the way, 17.4 pH. I think it's condition 1075 heat treat. Um, 17.4 is notorious for changing its shape. It warps and it distorts when you machine into it, particularly if it's been heat treated and everything. And the hole in this bar was off center, 500 and I think it's about 540-ish thousandths. Can't remember the exact number, and so being off center in the stock too would even increase this possibility. But apparently that didn't make any difference on this material. So kind of got lucky, but you never can be sure. You have to kind of account for that. I'm going to talk about that a little bit in the setup and planning of the job and what I had planned to do. But it turns out I didn't need to do it at all. Got lucky. But if you didn't prepare yourself for it, then you would have just the opposite, and it would be kind of like things go wrong, and then you can't recoup from it. So anyway, let me take this off of the fixture. Let me back up the tailstock here. See the plug. You can see that it didn't really change because the plug isn't even tight. To get me a hammer here or something to just tap this out of here. See, it's not even I was afraid that this was going to close down on this diameter, and then I was going to have to expand it and then finish the bore. So I left the bore 50 thousandths undersized here. And it would have been real convenient because I'd been done with the parts now if I hadn't have done that. But if it had distorted, it would be really hard to straighten this out. And you'll see when I explain it in the planning of the job that I did plan for a device to do that. But I hadn't made it, fortunately, yet, so I didn't need it. These small 832 screws out of here first. And then take the half 13. See, it isn't really tight. I could tighten it more, and maybe I could even show you here. If I tighten it too tight, I don't know if you can see that, but I can see it moving the part outward right here. And that's what I didn't want to do. And I also didn't want them to vibrate out of there and hit the milling cutters as well. So I put this little 832 screw in here to prevent that from happening. So I hope that kind of answers everybody's question there, because there was quite a few comments on the machining video of this about that. Okay, now the part, you can see the part is loose on the fixture now. Now I got to get some gloves on because there's some burrs. I want to cut my hand. Let's take the part off the fixture. And then I've got to change the whole setup over. So I'm going to get the view out far here so you can kind of see what's happening. I'm going to rotate this around. I don't know what the best way to do this. Let's see how I can just wiggle it off there. Trying not to jerk this off the fixture and hit my hand on the tail center too at the same time. I really shouldn't be doing this. My back has been bothering me. But I'm gonna go for it. All right. So this is the final setup for this part here. It's I made these rings, and like I've explained about the setup information. So this one here, this is behind these plastic pieces and on the steady rest, but it's actually identical to this ring here, and the part is bolted on there with these 1/2-13 holes, and the rings fit rather nicely in the on the OD of the part, and so I'm boring out this hole to finish size. And you can kind of see that piece of aluminum here that I've strapped on the part with these hose clamps. And the reason for that is this part would vibrate a lot. Let's go over here and look at this. Let me get something to tap on it here. If you just listen to these. I don't know if you can hear that. And so I have to bore about 50 thousandths of an inch out of the bore here because I left it undersized. Because I was afraid cutting this slot through here and relieving all of this stress I thought would be in the material. It would I kind of thought it would shrink in size and I'd have to straighten it. Which I don't know what part when I'm putting this in the video, but I'm going to explain that I designed a device to expand this with a hydraulic interpack cylinder, but it turned out I didn't need it. But you never can tell what's going to happen, and so it could have possibly been a problem, but it turned out it wasn't a problem in the end. So anyway, I'm boring it out with this. This is a silent bar with a kind of a offset head on it, so I could clear these extensions back here. This is a Capto 8, two Capto 8. I think they're 120 millimeter extensions to a Capto 8 silent bar, and that I think Paragon or somebody makes that head we're using there to get the offset enough to where it would clear the OD of those extensions when it goes up in the bore. The bar's about 25 inches long. 25 something. I had to be a little longer than the part because the part's sitting back in this ring thing here, about a little over an inch. So in order to clear the face of the spindle up there when it goes in there, it had to be that long to get to the full length of the part. I think that's about it for this video. It's kind of getting long, and I don't want to, stress your attention span out too much. The boring operation is just you just keep rerunning the bar. It takes a little bit of quite a few passes on the finish pass to get it out to size down at the end of the part, because the intermittent cuts tend to break down the insert before you get there. But other than that, it's not really a big deal. It takes time. So I think that's about it for right now on this part. As I said, I've got other things I'm planning on doing. I want to make a I've kind of switched into this DJI Action 4 camera because I kind of like this camera, but I don't have a waterproof case, and I've got a few more ideas on how to make that even better so we don't see all that coolant in the the picture, the images. Maybe, I don't know, I got a few ideas that might work for that, although the air works pretty good, but the coolant is kind of dirty in the Mazak too, and a cleaner coolant would help too. So anyway, thanks for watching.